We all know the importance of a strong foundation. It's the bedrock of any structure, literally. But what supports the foundation itself? That's right, it's the soil beneath our feet. And just like we wouldn't build a house on shaky ground, we can't erect structures without knowing the soil's strength. That's where soil testing comes in. It's the detective work we do to make sure the ground can handle the load. Soil testing is crucial in construction and geotechnical engineering. It reveals the secrets hidden beneath the surface, giving us a clear picture of the soil's properties. One of the most critical aspects we need to understand is the soil's bearing capacity. This tells us how much weight the soil can support without failing. Imagine building a skyscraper on soil that can't handle the pressure disaster waiting to happen. Soil testing helps us avoid these costly and dangerous mistakes. By understanding the soil's bearing capacity, engineers can design foundations that are safe and stable. They can determine the appropriate depth, width, and materials for the foundation to ensure the structure stands strong for years to come. Whether it's a small house or a towering skyscraper, soil testing is the first step towards a solid and reliable structure. Let's dive into the world of soil testing with one of the most common methods used, the Standard Penetration Test, or SPT for short. This test is like taking a coarse sample of the soil, but instead of using a drill, we use a hammer. Intrigued? Let me explain. The SPT involves driving a thick-walled sampler tube into the ground using a standardized weight and drop height. We count the number of blows required to drive the tube a specific distance, typically 12 inches. This number is called the N value. Think of it as a measure of the soil's resistance to penetration. Higher the N value, the denser and stronger the soil. Now, here's where the magic happens. This N value is directly related to the soil's bearing capacity. Engineers use established correlations and formulas to estimate the bearing capacity based on the SPT N value. It's like having a secret code that unlocks the soil's hidden strength. The SPT is a relatively simple and cost-effective method, making it a popular choice for many construction projects. While the SPT gives us a good initial understanding of soil strength, sometimes we need a more direct approach, especially for larger structures or when the soil conditions are more complex. That's where the plate load test comes in. This test is like putting the soil through a real-life stress test, simulating the actual load of a foundation. Imagine this. A steel plate is placed on the ground, and then we gradually increase the load on the plate using hydraulic jacks or weights. As we increase the load, we carefully measure the settlement or deformation of the plate. It's like watching the soil compress under pressure. By plotting the load versus settlement data, engineers can determine the soil's bearing capacity. They look for the point where the settlement increases significantly, even with small load increments. This indicates the soil's ultimate bearing capacity, beyond which it will fail. The plate load test provides a more realistic assessment of the soil's behavior under load, giving us greater confidence in our foundation design. Now, let's talk about a more sophisticated method that provides a continuous profile of the soil's properties, the Cone Penetration Test, or CPT. This test involves pushing a cone-shaped probe into the ground at a controlled rate and measuring the resistance as it penetrates the different soil layers. Think of it like taking a detailed X-ray of the ground. The cone penetrometer is equipped with sensors that measure the tip resistance, sleeve friction, and pore water pressure as it moves through the soil. This data is then transmitted to a computer, generating a continuous profile of the soil's strength, density, and other important parameters. The beauty of the CPT is its ability to identify different soil layers and potential weak spots with high precision. This information is invaluable for designing foundations, especially in areas with complex soil conditions. The CPT is particularly useful for projects involving deep foundations, embankments, and other geotechnical structures. Section 5. Back to the lab, unveiling soil secrets. While field tests like the SPT, plate load test, and CPT provide valuable insights into soil behavior, sometimes we need to bring the soil back to the lab for more detailed analysis. Laboratory tests allow us to recreate specific soil conditions and perform controlled experiments to determine the soil's engineering properties with greater accuracy. One common laboratory test is the triaxial test, which measures the soil's shear strength under different confining pressures. Imagine squeezing a soil sample in a cylindrical chamber and measuring the force required to cause it to fail. This test helps us understand how the soil will behave under the combined load of a structure and the surrounding soil. Another important test is the unconfined compression test, which is simpler but equally important. In this test, we subject a cylindrical soil sample to axial compression without any confining pressure. This measures the soil's unconfined compressive strength, a key parameter for foundation design. Think of it as squeezing a marshmallow, the amount of force it can withstand before collapsing. Finally, the direct shear test measures the soil's shear strength by applying a horizontal force to a soil sample until it fails along a predetermined plane. This test helps us understand the soil's resistance to sliding or shearing, which is crucial for slopes, retaining walls, and other earth-retaining structures. Section 6. Different soils, different strengths. Typical bearing capacity values. Now that we've explored various soil testing methods, you might be wondering, what are some typical bearing capacity values for different soil types? Well, the answer is it depends. Soil bearing capacity varies greatly depending on several factors, including soil type, density, moisture content, and the presence of groundwater. As a general guideline, here are some typical bearing capacity values for common soil types. Rock greater than 400 kilopascals, which indicates a very high bearing capacity. Gravel and sand, between 100 and 400 kilopascals, showing a high bearing capacity. Silt ranges from 50 to 150 kilopascals, classified as medium bearing capacity. Clay 25 to 100 kilopascals, which is considered low to medium bearing capacity. Keep in mind that these are just rough estimates and actual bearing capacity values can vary significantly. It's crucial to conduct proper soil testing and consult with a qualified geotechnical engineer to determine the appropriate bearing capacity for your specific site. Section 7. Playing it safe. Estimating safe bearing capacity. Determining the safe bearing capacity of soil is like calculating how much weight a bridge can handle before it risks collapsing. We need to be absolutely sure that the soil can support the load of the structure without any risk of settlement or failure. The process typically involves several steps. 1. Site investigation. Before we even think about building, we need to understand the ground beneath us. This involves reviewing geological maps, conducting site reconnaissance, and performing preliminary soil tests to get a general idea of the soil conditions. 2. Soil sample collection. We need to collect representative soil samples from the site, typically using boring or test pits. These samples are then taken to a geotechnical laboratory for further analysis. 3. Laboratory testing. In the lab, we perform various tests, such as those mentioned earlier, to determine the soil's engineering properties, including its shear strength, compressibility, and permeability. 4. Applying formulas. Based on the laboratory test results and established geotechnical principles, engineers use specific formulas and calculation methods to estimate the soil's ultimate bearing capacity. 5. Safety factors. To ensure a conservative design and account for uncertainties in soil properties and loading conditions, we apply safety factors to the ultimate bearing capacity. This gives us the safe bearing capacity, which is the value we use for foundation design. Section 8. When the earth moves, factors affecting bearing capacity. Soil is not static. It's a dynamic material that can be influenced by several factors. Understanding these factors is crucial for accurately assessing bearing capacity and designing safe foundations. Moisture content. Water plays a significant role in soil behavior. High moisture content can weaken the soil's strength, while dry soils tend to be stronger. Think of building a sandcastle on a dry versus a wet beach. The dry sand provides a more stable foundation. Compaction. Compacting the soil increases its density and, consequently, its bearing capacity. Proper compaction is essential, especially for fills and backfills around foundations. It's like packing a suitcase. The more tightly you pack, the more weight it can carry. Soil structure. The arrangement of soil particles or its structure also influences bearing capacity. Well-graded soils with a good mix of particle sizes tend to be stronger than poorly graded soils. Groundwater table. The presence of groundwater can significantly affect bearing capacity, especially for soils below the water table. High groundwater levels can reduce the effective stress on the soil, leading to reduced bearing capacity. Section 9. Building on solid ground. The importance of accurate soil testing. In the world of construction, there's no room for shortcuts, especially when it comes to foundations. Accurate soil testing is the cornerstone of safe and reliable structures. It provides the critical information engineers need to design foundations that can withstand the test of time and the forces of nature. By understanding the soil's bearing capacity, we can determine the appropriate foundation type, depth and size to ensure the stability and longevity of our structures. Whether it's a family home, a bridge or a skyscraper, soil testing is an investment in safety and peace of mind. So the next time you see a construction site, remember the hidden world beneath our feet and the importance of soil testing. It's the invisible force that keeps our structures standing tall and strong.